Yes, your computer works now.
All right. Has it actually been used like extensively yet, or is it just booting up?
I mean, it boots up and it loads the desktop, but we haven't done anything of it because when you
do have system work. Welcome everyone to the meetings. Would you please, anyone who is on connection, try to speak up and that will test that we can hear you here.
Testing.
Okay. Landon, many thanks for the test.
Yes.
So everyone is very welcome to this series of meetings. We are going to process the manual for non-adiabatic couplings. Later on, we may set up a dedicated meetings for theory, but right now there will be a little bit of theory, I think, in presentation by Landon, and rest of us will be practitioners, just sharing practical skills. The goal of our meetings that everyone can efficiently and independently run non-adiabatic dynamics, which targets to follow what happens to molecular material upon promoting system into the excited state. And it will take at least 2, maybe 3 more weeks. But the meeting today is most complicated, most critical, and it is kind of a barrier that we need to get through. So the plan is as follows. Before this meeting, we discussed that it is highly strong advice to everyone to run molecular dynamics for your preferred models. By now, it is expected that everyone has a directory with a trajectory of molecular dynamics. And the skills, the instructions that we were provided today by all enthusiastic presenters will help us to proceed with computing so-called non-adiabatic couplings. Those couplings are useless by themselves, by them all. They are only input for next stage computer codes, which would allow to compute something really cool and unique. But this is a very computationally intense procedure, mostly computationally intense, and it is time to start doing it because there will be history of success and failures. And if, for example, if I'm visiting it for the first time and I'm thinking, let's do this for the whole month and only then start doing something, it will not work. It's better to start practical things right now. In the light of this little announcement, while listening to the speakers, I'm inviting you to chase them. So while the speaker is delivering something, please ask questions. Taking into account that likely you need to repeat whatever the speaker is offering. And if some technical details are skipped or something is not clear how to do, ask right now. Where are the codes? What is the path? What is the exact command? And speaker may answer by words or just by making quick notes in PowerPoint slides or just typing things in the chat line. So we do have 10 presenters. If you do 5 minutes per presenter, technically it looks like 15 minutes, but I think we will go over 2 hours because there will be questions. And do not lose your temper and energy until the last speaker, because David is listed last, but he is very not listed. The skill that he's presenting is critically important to those who is interested in magnetic materials and spin fluid procedures, spin fluid opportunities. And his slides, as I'm aware, are quite brief, and especially encourage everyone to ask questions today. We talked to him briefly, and he's aware that everyone is welcome to chase him after this. So from now, and when we are done, there is a tentative list of presentations for next week, but let's process them and volunteer after we're done with talks today, which are much more important. Without today, there is no tomorrow. So this first one, oh, I need to enable the London is host. Okay, so if you can do it quicker than me and allow you to be we're gonna co-host.
I didn't realize I was the host. I think I just made you the host.
You made wrong me
Oh,
host. You made me on the.
uh-oh. Now I don't have the power to do it again.
Here is my alter ego. I'm not yet a host. Let's check. Yes, you did good. Thank you, man. Let's just so you can start sharing the slides and presenting, and as we go, I will make others host. Okay, floor is yours. 5 minutes are yours, and then everyone will check you.
All right. Hi, I'm William, and this is I'll do the density of states. So here's some of the code that you first need to input. You need to run it through batch photon, and then it'll tell you that there's 2 types. And then after doing this, it'll give you some information back. You then do more outcar, and then it's going to give you a bunch of numbers. From there, we only really care about where it's talking about our K points. We then take these values, insert them into bi-states, and then if we want to, we can just to make it easier to read what these numbers are, we can then sort them by the energy by doing sort minus GK 2 states, which the 2 says to sort it by our second column. But if we wanted to organize it by 1 or 3, we just change to 2.
What is the G doing?
That I'm not sure. I know the minus is going to be sorting it from negative to positive. But
I just don't know what the G option does for sort. The minus K is telling is the column.
yeah.
And it automatically does negative to positive. That's just the default.
G is general numeric sort, so it compares according to general numerical value. Then K is month. No, wait, no, never mind. That's a different thing.
K does columns. Is telling you which column to sort by.
Yeah, K is for key.
And then we take we run this, put it in a bin, and And then it's going to ask for a number of values. So like we can see back, or is asking for our min energy or max energy. So that's where we want to look at our Fermi energy and alpha beta. That stuff can be found in this previous part where gives us our Fermi energy and then alpha beta. And then you give it the number of atoms you want, the number of electrons, and then it'll say that for magnitude, you just put 1, and then for gap bulk, you also just put 1. And then just to check some stuff, you do LS, LT. And then to graph this, you want to do new plots, and then the PS2 PDF to get a PDF of this, and then you can see it. And then on the left side, where list your files, it'll be the density of states PDF. And then here's what the system that we're plotting. It is sulfur and then 3 hydrogens. And then this isn't what you'll get, but this is the band energy of the sulfur and 3 hydrogens. And then lining that up with our neutral or our natural or neutral states, you can see that we have our 10 and 11, 12 and 13, and then our 14, but then we don't have a second one in that 14 range. And then if we were to removing 2 electrons, we see that then this state is now just completely empty, like here. And if we were going to add 2 electrons, we would then end up with this band here being completely filled. Any questions?
Okay, please join me in thanking Yulun. Did I miss how you change the lens? Change the number of couplings?
Oh,
You can tell by words if it is not sure.
so yeah, I'm looking at your file.
Recording posted, maybe you need to keep recording. Thank you. I think now it is going on.
So here on the right, you can see that like before we had this band, or was like halfway filled, and then this second part, when we were moving 2 electrons, you can see that this isn't filled at all anymore in this band gap, which then I marked by line. Dr. Keelan and I marked by lining these 2 figures up, so like the 14 would match the 14 on here, and then just added a clear dot to show that it was removed.
Some of today's attendees were not visiting last meeting. So can you, when you were introducing this figure, can you just define what it is?
Oh, okay. So this figure on the right, it's giving your band energy as a function of your momentum with the K points. And I guess I'm still not exactly sure what a K point is yet, besides working with reciprocal lattices. But you can see that there is some sort of relation. There is a relationship between the 2, and then it does have some, I guess, sinusoidal part to it, where it does have here some wave.
Okay. May I ask you to help viewing and just maybe define in 1 sentence what is momentum dispersion?
So for momentum dispersion, difficult to how to define that. So we define multiple key points in the specific direction and calculate this value. And what else we can understand from this?
Anyone else wants to try? Hadassah, you have enthusiasm to try?
I guess I think momentum dispersion, I think it's like we have a well-defined position, we don't have a well-defined momentum. So
No. Here on the x-axis, we have defined momentum. And we show how the energy of an orbital depends on the momentum, or on velocity of the center of charge of the orbital. For today, this figure is marginal in a good sense. We just do not have time. But in the past, in the group, we have competence to run non-adiabatic dynamics where the excitations of this electrons and hole change not only orbital, but also change the value of momentum. And it is a little bit more complicated and advanced. So maybe in the future we will pick up as a group and go forward. But right now, William is the only one who speaks about key points. After him, everyone will believe that momentum is equal to 0 in the center of the line.
So for multifocal dots, I guess, to work, right? Those, what are those? Just key points.
Those are the, I guess what the electrons when they're filled. So when they're solid, or if they're there, that means like we have, since there's like 2 at this point, we have 2 over here. And then later on, or here, we have 1 dot, like this is the one, and it's not completely filled by it.
So just to satisfy the curiosity, if you want to be very rigorous, we need to fill these dots for each value of momentum. But if you be boring, numerically expensive, and boring coherence, so instead of doing like 40 key points, you can just did 2 most interesting from his point of view, from my point of view, and explored how density of states will reflect this key point, but for more adequate on this.
I have another question. It was one on the previous slides where you had your sort. I'm not sure I understand how that command download. I'm not sure I understand how that command works. It looks like what's printed is like it's 1 1 2 2 4 4. So they're like it's why is that?
That's from, there's different K points, so it's like 1 from the first K point, and then 1 from the second K point, and then onwards.
So that's what you're talking about.
But if you look on his orbital number 10, which is home, there are 2 homes, one for velocity going forward and another for backwards. And if one would make a fair distribution of K points, there will be like 40 homes. Okay. Yeah, many thanks for discussion. Any questions to you? Questions 1, questions 2, questions 3. Okay, so thank you. So from now we reduce our focus only to momentum equals 0, which is more adequate for chemistry. And next speaker is Joseph. So the logic of today's talks, not each of the talks is on non-adiabatic couplings, but it is kind of fundamental steps leading us to non-adiabatic couplings. And way how it is computed is very much related to the way how we compute absorption spectra. So there will be a couple of speakers who just refresh our skill of absorption spectra as a fundamental for next step in non-adiabatic couplings.
No.
Yeah. So room my clock.
Yeah, so if those who are on the line do not hear, just complain and we will enable 6 mics and it will be a lot of
Perfect. All right, so you're working on calculating the absorption spectrum and oscillator strength, or we'll use the oscillator strength to calculate it for a given molecule. So just for like a little bit of like theory or background, to be able to calculate the absorption, which is the equation we see down at the bottom, we need a few other complicated equations first. The first being the transition dipole moment, which, if you're familiar with just a regular dipole moment in physics, to my understanding, it is kind of like that, related like between two different like states of your quantum system. So it can loosely be understood as that. And then for the oscillator strength, which is based on the transition dipole moment, it is related strongly to the probability of a photon being emitted or absorbed in a quantum transition. The other way that that energy would be like a thermodynamic process, so just like vibrations and whatnot. So to be able to calculate absorption, we need to work on calculating both of those two values. To do that, we have to first assemble some of the input files. So as you can see here, we have to start by placing our outcar, WAVECAR, and then a couple executables into our directory. And we have to create this file called the input overlap, which basically tells us what bands and what orbitals that we want to consider. And you can see the example of that file over left. So the first number is like the lowest energy level or the lowest band, and then second number is the highest. And then the third number is a placeholder, or maybe it's an increment. I think it might be an increment. So calculate every band or like every other band, whatever kind of pattern you want to do. And then to actually prepare the files so that we can run to calculate the oscillator strength, we have to produce this energy pop file, which stores the band energy level and for the electrons, or for the orbitals, sorry. And we get that from the outcar file. Then when we run the energy pop executable, it will basically select all of the bands that are empty, I believe, that we want to pay attention to. Then to actually run the oscillator strength program, we have to change our dependencies. So you just do that with this module swap command, and then we can run our oscillator strength command. And then we have to do a little bit of file swapping. So we move the oscillator strength output file just to some extra file. And then we select only the band transitions from a like fully filled orbital to an empty orbital using just the grep command. We move that back into the oscillator strength file. And now the oscillator strength file will contain only the orbitals or transitions that we're interested in. And you can see at the bottom an example of what some of the lines in this file would look like. And then some of the actual headings for it, I guess. So what bands, the oscillator strength between those two bands, change in energy, and the populations. Now to actually create the absorption spectrum, we have to first figure out how many transitions we actually have. So you just do that with this WC command on the oscillator strength file. And in this case, I had 216 to worry about. We then run this spectrum imp3 file. And it's going to ask you the number of transitions that you have, the min and max energy difference, which I chose to be 0 to 5. Pretty sure that's because that relates to the visible light spectrum in terms of energy. And then we enter like the width of each line because in the two graphs on the lower right, as you can kind of see, it's a smooth graph. If we had chose the width of each line to be 0, we basically end up with more of a bar chart looking sort of thing. Sort of basically adding in some amount of error or broadening to our data to make it match like experiment better. Then we have to enter the HOMO, and then that will run, and this creates a spectrum file. Once you have the spectrum file, you can go into new plot, and down at the very bottom, you just have to run this load command, which runs a script that will actually produce this PDF. It's actually a PS file, and then we have to convert it to a PDF, just like how Will had to do. And then we can get our absorption spectrum as a function of the energy, as you can see in the lower right. So I just included those for a couple of the models that I'm working on. That is what I've got.
Okay, please join me. Thank you. Any questions? Or constructive criticism, if you found any wrong steps or wrong explanation of correct steps.
You go back to the first slide. I think it was the first slide. Yes. Yeah. The C is the constants. Yes. So I will adjust this so that when people review it later on, it's correct. There is a bunch of constants out in front that I didn't include just because it kind of takes away its little eyesore. But yes, that C has a bunch of stuff combined.
And then the star, the complex conjugate.
Yes, yeah.
So any more questions in the?
What's the dx, dy, dz you showing us in the oscillator strength file?
That is a great question. I'm not sure about
Come on,
that.
you're sure.
I am pretty sure.
Let's go to your questions.
Yeah, so I think what it would have to do with is this transition dipole moment is a vector. And it commonly is represented with a D, I believe, which is why we would have dx, dy, and dz. So it's just looking at the individual components of that vector. I think.
You're satisfied? Okay, good. Anyone in the one-to-one in person?
So with the dx, dy, dz, what does it do in Cartesian rather than spherical? Because usually when integrating, I guess something like this, you think spherical would be easier.
That I'm not super sure of why it would be in Cartesian rather than spherical. I guess if we're making a computer do it, the computer doesn't care if spherical or Cartesian is easier.
Yeah.
Maybe.
I think I have a hypothetical answer. The simulation cells are periodic. They are like boxes with borders rather than spheres. If I would do it in like infinite space, maybe it would be reasonable. But here, this code uses periodic boxes, and it's more reasonable. If we are done with questions in person, maybe there are questions like they will have to ask your online question in person. You can talk. Okay.
I guess so. Going to the questions in the chat, what does changing dependencies mean? So I'm guessing you're referring to this module swap command. So what that is doing is changing the preloaded background files that are going to be basically doing all of the work of actually calculating things and running code. So we have to change basically what kind of underlying code we're using to run our code. It's basically what that's doing.
Perfect. I'm so happy. And as a growing star of programming, is there any single word to describe all this whole description?
I don't know. Off the top of my head.
Libraries?
Yeah, I get, yeah, you're changing libraries. That might be a better way to say it. Yeah. I guess I'm not.
I think next two questions are the same. You can just read them one after another and then answer at once.
I guess I'm not sure what you're exactly referring to.
This one. So
Yeah.
Yulun was showing a list of orbitals, their energies and occupations, and he created them by hard manual work of copy and pasting from WAVECAR. And you did some tricks. So do you do this? Is it the same information, and how your procedure differ? Like compare.
Yeah. I'm pretty sure it's the same information. And yeah, it's just showing the band, the energy, and then its occupation. So basically, the way that I did it, I guess, is going through this outcar file and then using the grep command.
This is basically the same what you did. You ran extract energy port, which is independent. If you work without this grep.
Oh, yeah.
And can you go one slide back? So the input overlap is an input file that is being inspected by extract energy, and this extract energy program looks through outcar file and extracts energy starting from first and last orbitals that you mentioned in the input overlap.
Yes. Yeah. That'd be a better way to say it.
Did he answer the question you answered to Jordan? More questions to Jordan. More questions. One. More questions. Three. More questions. Oh, forgot how to three. So we are continuing to set up fundamentals, and the next presenter is Nahar Keya. Here we need to share your screen. And
Yes. Are you able to see my screen?
yeah, we can
Okay.
see.
Yeah. So it seems like that my slide almost overlap with the second speaker. So I also showed how to do the calculation for the absorption spectrum. So basically, the thing he didn't show that that one I will emphasize here, that in the basically for the absorption calculation, spectral calculation, we need post-curve, out-curve. I didn't write the WAVECAR. We need WAVECAR file also, and here I wrote the state file, because if you did some calculation before, then you can copy the files from your previous folder. So that state file actually contains the band energy and the electrons which are shows those are occupied or unoccupied, and that one we need to copy. It's like CP means copy the state file as an energy port, and also we need like energy overlap. That one already showed by the previous speaker. So in the input input file, there is L wave, that one, and we need to make sure that that one is true, because this one is like when they are doing the calculation, they did some analysis, like the WAVECAR file, like in the WAVECAR file, like they are considering that WAVECAR function there in the WAVECAR file. So because of that, we need to make sure that this is true. We need to change the inker file, and after that, because we already have these things, like let me show here this. Okay, so yeah, like copy state file in as an energy pop, then we can see the energy pop that one. And if we want to see the what's inside the energy pop, because that one is the same, so that's why I didn't show here. And because this calculation was done in the photo, so if we use this command, and then we can able to do the next step, like doing complete the calculation almost. And after that, when we are able to see that OS are done, that means OS strength, that file already generated, then using that file, actually we are able to do the plotting for the absorption spectrum. So here you can see that in like this one, when I need to go down, just these things. Here we can see 1, 2, 3, 4. So here you can see that this if we want to look at what's inside in the OS strength file, in there the first column and the third column is for the oscillator strength, and that one is the most important things for our calculation. And the fourth line is energy of transition. Energy of transition, actually the difference between the initial what should I say, the initial orbital and the final orbital, it's not correct, but the first column and the second column, the difference is the energy of transition. So basically we need the third column for doing our calculation. And then when we complete the things, like here I didn't show those things, like here it's all the same. And yeah, so after that, so when we can see the OS strength, and we need to for the spectrum plotting, we need to use this red mark, that line. And then from the OS strength, we know the number of transition and energy difference from the energy pop, and we know the HOMO from the energy pop. After that, we are able to get the spectrum file. And from that, if we use this like Gun plot that line, and then that command, then we are able to plot the spectrum, like absorption spectrum graph. So after that, that P is to PDF, that one we need to convert that one into a PDF file. And because of that, we use that command. Okay, so here we are able to see this is like Fij, that one is the oscillator strength, and this is absorption spectra graph. And from that we can see that if in the left side, this one, you guys can see the arrow, and that one is like if we say this one is the peak A, that one shows the lowest transition, but lowest transition energy, and it also shows the highest and because it shows the lowest transition, that's why it's I forgot that term. lowest transition energy. Yeah, it's like a it's or seems like that it shows the brightest transition occurred here, and in other are shows the darkest transition actually. If I'm wrong, then professor and tell me like this. And I didn't add the non-adiabatic term, non-adiabatic coupling, those things. Professor. Yeah, like lowest transition energy here, and but highest intensity, like this one. Professor.
I muted when you went to talk. And
Did you?
Yeah.
Okay, now I invite everyone to.
Yes, yes.
So any questions to Keya?
So yeah, you showed you had this in both these spectra in electron volts and then the other one in wavelength. What's the I don't know if you mentioned this. I but how do you do that? How do you display them in transition energy, and how do you display them in wavelength?
Actually, and just I because today I didn't explain these things, only absorption, transition energy. This.
But here, where does one save information about wavelengths and nanometers?
Yes, same. Oh, same.
Where in which file, in which column, wavelengths is saved? Is it what Adam is asking?
yes.
We are using the spectrum file, like spectrum. We are using this same spectrum file for plotting these two graphs, basically.
So which column?
Which column? That third column.
Third column is intensity. Second column is transition energy, electron volts.
Just 1 minute.
There are total 3.
Yeah.
So not oscillator strength, but spectrum.
Oh, sorry. This is energy of transition.
No, not here. You're showing oscillator strength, but for those images, one needs spectrum file. Right? And first column is
Makes sense that 2, 3, 4.
right.
Thank you.
More, yeah. And of course, the question is satisfied with the answer. Are there more questions to Keya? Questions 1.
There is some echo.
Question 3. No, let's thank Keya once again. So now we are slightly switching gears. 3 talks up to now were all made for static positions of ions, where ions are not moving. And going forward, the briefly non-adiabatic coupling is response of electronic structure to motion of ions. And there are several ways how to include motions, how to include trajectories along which we compute non-adiabatic couplings. Typically, we do it along ground state heated molecular dynamics, but there are alternatives, like dynamics in good excited state, or one can look at trajectory for chemical reaction. By now, we do not have much of the results and plans to do it, but it's possible to do several ways of trajectories. And it is a connection to the presentation by Yulun, by Dr. Han. So on one hand, it is connected to our non-adiabatic things. On the other hand, it is a standalone skill that is critically important for any chemist who is looking for chemical reaction. It's a way to extract the transition state between reactant and product. Okay, even for yours. And please unmute your microphone. Yes.
Okay, so I guess if you guys are interested in chemical reactions, then it is very important to do the transition state search, because this kind of calculations will give you the reaction barriers and also, give you some insights about your reaction mechanisms. So to do these calculations, you need postcard and outcard from geometry optimization calculations for initial and final structures. You also need some standard input like in-car, pod-car, and key points. And also, of course, the script for job submission. And the third step, I guess, this is quite important because you need to have some basic knowledge about your reaction pathways. So if you have some knowledge, then you can input some reasonable initial gas structures, which can be used as intermediates to bridge between initial reactant and final product. If not, then I guess you can use this script just to do a linear interpolation. But I guess this is not very good. But still you can do it. So here the IS means the initial structure postcard, and FS is just a final product postcard. And N is just the number of intermediates you want to insert between initial and final. So after we run the script, we'll generate several subfolders, and each subfolders will have some postcards. And I guess you need to make sure these postcards are reasonable. So here is a output. And then finally, you need to put your initial and the final postcard and outcard. First, put the initial reactant postcard and outcard into folder 00, and put the final product postcard and outcard into folder 04. So here we assume we insert 3 intermediates. If you are inserting more intermediates, then change the folder name to N+1. And the left side, this is just an in-car. And then there are several tags we need to focus on, like Potium, like this one, and also IOPT. So basically, the IOPT just select different kinds of optimizers, and some details can be found in the website, like I show here. And the right side, this is the script for job submission. So I guess we need to pay attention to this line. So instead of our traditional job submission, we use a different version of WASP. So if your job is successful, then you can use this command to process output. So here is an example. So basically, the second column, this is the false. The third column, this is total energy. And the final column is the relative energy. So as we can see, we have a transition state here, about 5 electron-volts. So here is another example. So basically, this is a transition state search for peptide bond formation. So basically, we insert 7 intermediates, and the middle one, this one, is just a transition state. So that's it.
Okay, please join me. So any questions in person or online?
So I have 2 questions.
Yeah, go ahead.
So first, this x-axis reaction coordinate you calculated later on in MATLAB or somewhere else, correct? Or
Yes, you can do it, but I guess in the VTST code I shared before, there is a standard script to process this kind of data.
So what is x-axis here?
This is just a reaction coordinate.
No, I know. That was listed in previous study or no? In the data that you generated?
So basically, it's some kind of a code in this kind of folder.
Mm-hmm.
But I guess I just need to double check the script name. But
Okay.
But it is there.
Okay, and in slide 2, I didn't get LIS and FS. How did you assign them?
It's just the postcard file for your initial reactant. You can name it whatever you want. I just gave it the name IS.
I get a little confused. Could we assign a file to a name? IS equal postcard?
Doesn't matter. I can do this one.
That was I had another. Okay, I get it.
So, I mean, likely IS and FS is not like its initial state and final state abbreviation, right?
Mhm.
Mm-hmm. Okay, I didn't use this comment before assigning a file to a character, to a variable. Okay, I got your point. Thank you.
So, Dr. Han, I have a question.
Go
So,
ahead.
you said we need to have the postcard and outcard of the initial and final structures. For this case, for example, you mean by initial, you mean the postcard and the outcard file of the 2 amino acid, and the final is the dipeptide structure?
So let's look at the final slide. So basically this is the initial structure. And this is the final structure. You need postcard and the outcard for initial and the final.
Okay, thank you.
Any questions in the room?
Could you re-go over what the columns in the DAT file are again?
This one, right?
Yeah.
So basically, I guess the second column, this is just your force, because this kind of transition state search is force-based. And the third column, this is total energy, and then the final column is relative energy with respect to your initial structure.
So, Dr. Han, you for the last plot, you considered the final column as the y-axis, correct?
Yes.
And for the x-axis, you said by generating or by executing this comment on top of this slide, it will generate another file that has the coordination inside of it, yes?
Yes.
Okay, thank you.
So what's the name of this file that contains values of reaction coordinate?
I need to double check, maybe distance or something like that.
Okay. If there are no oral questions, let's look through the chat.
There's some question about AEB. I guess it's largely the elastic band.
A non-elastic band. Oh, okay.
the second question, why is POTEM equal to 0 and SW equal to some very large number? So I guess this is a requirement for the code. So basically, the VTST is those guys who write the script. They have different version of optimizer for VASP. I guess to enable their version of VASP, you have to set POTEM to 0. Why SW equals to a huge number? Well, because this kind of calculation is very difficult to converge. So here I'm just trying to make sure we have enough ionic steps.
Okay.
The one submit job for all sequence is always manage job system. No, I guess you just need to submit once.
Okay.
Yes, you can submit this kind of job for limited number of steps and then restart. Just convert count car to postcard again.
Okay.
So, Dr. Han, can you please go to slide number 2? So for the n number of intermediate you want to insert, what does it mean, number of intermediates? So how we should specify the correct number?
Well, this is just your personal choice. Because this number differs from system to system. Like here for the peptide, we use 7.
Yes. So how you understand it is 7 for this system? Basis on base of what information you
okay,
say
so
that.
Maybe this is not correct, but this is what I did usually. So basically I start from a very small number, like 2 or 3 intermediates. Then I just increase systematically until from your calculations, you can see some trend if your calculation is convergent or not.
I see. Okay, thanks.
Yep.
So the larger number would be better, but it would be too expensive. So when one person finds a balance between numerical cost and precision, right?
Yeah, makes sense.
I guess if you have some solid knowledge about your reaction pathways, then you can increase your number of intermediates. Otherwise, it's like you artificially fix your reaction pathways by providing too many intermediates, which is not good. So I guess there is a balance, between accuracy and efficiency.
More questions in person, online, or in chat? Questions 1, questions 2, questions requests. The next presenter is right here in the room, so it's Adam. And I believe in narrow sense, our today's session starts from Adam's talk. So he will teach us what to do if you have molecular dynamics trajectory and you want to start from there and go towards non-adiabatic couplings.
Yeah. So this job is it's pretty simple, but it really just feeds into the overall, I guess, theme of wanting to find those non-adiabatic couplings. So here's the general procedure. I knew last week we had a presentation where somebody had something like this, just a little bit more in depth, what you need for each of the steps. We want to optimize the geometry, feed the system for molecular dynamics, And I'll be talking about extracting these position snapshots from the molecular dynamics run. And then from those snapshots, you can calculate non-adiabatic coupling through a couple steps after that. But I think there are presentations today that covering that. So kind of why do we need snapshots? Well, here's the equation Landon gave me so kindly and provided kind of a good explanation along with it for calculating non-adiabatic coupling. We want to know the ionic position at each time step delta t. So if we have 1,000 time steps, we can expect to get exactly 1,000 postcard position files for that thing. As you can see, it's P000, P001, and it goes up to P999 for 1,000, for example. And once we have the ionic position at each time step, we can solve for the non-adiabatic coupling with bscript, which again will be covered later. So in order to extract these, we first kind of have to do a setup. So we want to make sure that MD is complete. We want to make a new directory and basically copy over everything from D to our new directory. A new directory is going to be called snapshots. At least that's what I did. You can call it whatever you want. You're going to edit the postcard. And basically, this is just converting from class5 format to class4. You're just going to delete the 6th line, which is going to give the elemental composition. You're going to keep those numbers still, of course, the 114, 124, 81, but you're going to get rid of the element identities. And you're just going to save that. Now you're ready to write your script. Here are the general commands that I use. These are just in my directory. You don't have to use these names. Just use this as kind of a reference. So it's just a single command that you use to grab those positions. First, you want to make sure that you don't have anything named P, starting with P in your directory. That's just going to make the script freak out a little bit. I'm going to run this bin outcard and postcard.pl. I know there are a few other scripts. I think there's like out to post. There are just a few variations of this that exist in Cori. And then after it finishes running, you can just kind of look at all the position files that you made with that. And now you can use these in finding that coupling with finding the WAVECAR each time step and extracting using the script. So yeah, that's it.
Okay, so so any questions in person, online, or in chat?
So do you only need postcard from your, and not postcard, just which files do you need for this from trajectory? Like
Ideally, you just copy everything. Just copy everything. It works. It works best that way.
So I guess you mentioned that there's like several different like scripts that could be like a similar thing.
Yes. I mean, the other ones, they're not as pretty as tilde bin, outcard, and postcard.
Okay.
They're like, there's another one that uses an underscore. There's another one that you find in like some like long directory in Cori, but then I believe they all do the same thing or something similar, but I'm not exactly sure when you use one over the other.
A comment making a connection between Adam's talk and Dr. Han's talk. The majority of scripts that we are using are, let's say, stolen, respectfully bordered from publicly disclosed. So there is a book of Professor Graham Henderson at Texas, who programmed this transition state search, and for the purpose of implementing the state search, in his group wrote several codes, like same as here we writing with the code, but we are not yet So we should help the rest of the world with doing them here. And they are open and public. And a lot of these .pl scripts are borrowed from this Texas site, and they are also happy to work with those. So this outcard and postcard and XDAP to post, they belong to the same group tools. Because that's powerful. Just giving credit to the authors. Yeah, let's keep on asking Adam questions. What is your program?
What do you do if MD takes more than one job to finish one run?
Oh, yeah. So you basically just make a new directory and name it like MD2 or something like that. Like you do sequential naming and just keep on doing it until you get your desired number of runs. And then you have to individually name the P number files, and there's a way to do that with a single command. You just enter the starting number. I believe. It's my biggest failure. Okay, yeah. What is the typical error and advice to avoid it? Well, so yeah, I definitely know my failure. So if you don't do this, if you don't format from boss 5 to boss 4, when the script runs, what it's supposed to do is it's supposed to like print out basically just all of the coordinates like one after another. And then you'll get a really long list. But if you don't do this, it's just going to be blank. You're going to be kind of left confused. And what makes that worse is that it's still going to make these P number files. So you're going to have a big mess of a directory, and it's not going to be fun. Additionally, you as David kind of asked me, you don't always get what you want when you run MD. You don't always get every single time step that you I guess desired or specified. Or sometimes you get more, sometimes you get less. Here I specified 1,000 time steps. I got, I think, up to 1,107, so 1107. So that's I got 107 or 108, I guess, technically more time steps than I really wanted. I'm not sure how to avoid that part, but yeah, I do know that you could just run. If you don't have as many as you want, you can just run it again and rename those files after that.
Okay. Thank you, David. Any more questions to Adam? Personal line or in chat line? Questions 1, questions 2, questions 3. Let's take Adam once too. So the next presenter is Hadassah Griffin, and she will she by being volunteer, she took the hardest task. So basically she covered several subjects more than was originally. Original plan was to split things on smaller things, but she covered the whole story, how to get from positions to couplings. And if any of us is trying to compute non-adiabatic couplings for the first time in the life, trying to follow what Hadassah will show is the good example to follow.
So I should just go through the entire arc, or should I? Okay.
Basically, if you want to narrow down our session to one topic, it will be your turn. So you have a great responsibility.
I can speed up the parts that are going to be explained or have already been explained.
Go ahead, whatever.
Yeah.
If you speed up, we'll stop you.
Okay, so I was tasked with setting up the view script to create multiple launchers from a single script. I adapted if you were like doing a non-adiabatic coupling without spin, and I'm guessing that's spin that where it's like, or it's a single state. So, that was based on molecular dynamic trajectory data, and it's one reason my presentation ended up being long was I understood that I had to successfully complete these non-adiabatic couplings and run the speed script, so I figured I had to do the entire thing to make it work, and it worked. But the base idea is an overview of stunning NERSC. We've submitted things to the SBAT or the compiler NERSC before. We have our SBAT script, and in this there's a bscript, which goes to another file which has all these commands, and in this there's a for loop which will execute commands multiple times for you as much as you need. So instead of you've already done your molecular dynamic calculations, I tried to do things in a different directory, so I didn't erase things in my old one. I found that I needed the WAVECAR, the XDataCar, postcard, and as Adam talked about, it has to be FAST4 format. I was also found out that car is very important. I didn't know that, and that caused some headaches. That's a mistake to be aware of. You also need oscillator strength calculations, and that's going to be covered later. So Adam's already covering how you go BAS5 to BAS4. Like you said, do the 4 snapshots. You already went over doing the trajectory things. This is one of the examples of another script if you want to just see like a couple individual timestamps, but it doesn't output the postcard in like a P number format. So this is just nice for like looking at debug. I ended up doing this one, which that's the same one you used, right? Okay, so we've already gone over that. So for the non-adiabatic couplings, without spin, you have to copy some templates. There's WAVECAR. There's also the couplings no spin. This is where you'll get the bash scripts for what you submit to the compiler, as well as the bscript itself, as well as some oscillator strength things that you need later. In the script itself, if you want to, you can comment out like whatever the version of the fast executable is. That may or may not have led to some debug errors in my scripts, but also you can modify the queue and the time as usual. In the bscript itself, things to edit. First of all, I guess you have your initial position step. Here this would be like, I guess, step 0 or where you want to start out. You manually name that. From there, you just have the step after that. So like in this for loop, you can modify where you're starting and where you're ending. And you can do different ranges. They'll help you generate coupling files of what you need. I guess one thing to be aware of, if you are debugging this, and you'll notice like there's all these remove commands in the process, it's possible that like this energy pop file, once you generate it, could be deleted if your script is running into error. So it's a good idea to make sure you copy that elsewhere. So you submit this compiler, it takes however long it's going to take. And this is going a little ahead of the story, but you'll get these intermediate data files. What has the coupling data? It's .gz MATLAB files. You transfer them to your personal system to analyze them. You can use MATLAB, and I think this is going to be covered next week more so, but I found out you could download MATLAB from NDSU, and there's this MATLAB website and how you can extract the files, and in the end you get these coupling files. But that's the overview. So any questions?
Okay, please join me in thanking Hadassah. Any questions in person? Any questions online? So it's better to ask questions now rather than admit that jobs failed half a year later. So
It's also much less.
right. So try to just look through slides that Hadassah has presented and check if you believe you can follow each step, and if something is strange or not clear, better ask now.
If you go one slide back, I think. One forward.
Yeah.
What is the 544 again? Go over that.
Yeah, so that's just the version of VASP. Dr. Blaine told me like every half or every half year, like they send an updated version. When Dr. Blaine helped me debug my thing quite a bit. I'm really good before that, so thank you. But you can't just like put a comment down, put a hashtag in front of it, and then it'll won't specify which version it is. You may or may not have to do that. It was just done in the process of trying to figure out why mine wasn't working, but
Okay,
yeah, so I just put it in there as like it's optional because I don't know.
just something to check.
Yeah.
Okay.
Anyone online? Or if someone is practicing similar couplings by different protocol, or if you see any divergence, or you have constructive criticism, please speak up. Like, well, I know that you tried different scripts on different platforms, so if you have criticism, please share your observations.
Sorry, what sort of observations do you want me to share? Sorry.
Just if you agree with those steps, or if something may look differently, just your feedback to what you saw and hear.
Okay, the other thing I noticed is when you it's a particular line, the for loop that goes from I106 to like 999. When you do this in NERSC, it doesn't entirely do this for you like in one go. So you would have to like always come back to check and then always change that number based on wherever the calculations stop.
Mm-hmm. Okay, yeah, thank you, Lola. It's an important practical advice. I think it is what Adam and David will discuss. Yes. So as soon as we start modeling large time systems, they may not complete within all time. And when we need to chop these 1,000-step trajectories onto smaller parts, which can be run in different subdirections simultaneously or one after another, but it should be taken into account.
How do you, so with the modification to the submission script, how do you determine how many cores how do you set the amount of cores you're using?
Not really sure. I'm new to parallel computing and series computing, so.
Any advice or experience?
Well, if you want to wait till mine, I mentioned it mine, but if you go to the next slide, you have it more or less covered by the blue box. That S-run line where it says 256 there. So that S-run line is normally in the submission script. And that 256 is the number of cores you're using. And it has to relate back to the number of nodes you use. It has to still specify in the submission script, which yours does not at the moment based on the submission script we showed and the B script we showed.
Yeah, here it is, and one node has 64 cores, so if you request 260, you request 4 nodes. Okay.
Yes, there was like a few different types of like output files, like types of output files as well. Can you
I think most of these, based on what I can see of the presentations that are coming, they may explain more of what's going on. Like, I know Landon's presenting us on like master equation. I don't know, I think the WAVECAR file will just be like the individual WAVECAR files for each calculation, but I'm not familiar with what all this being output is at this point. So.
And as a byproduct, so your second bullet point mentions view data for master equation, and it misses oscillator strength. So while running, it also creates probably what Joseph was asking. It recomputes oscillator strengths file for each point of trajectory, which will be slightly different. And in 2 weeks, David will, or maybe 3, will teach us MTPL method how to utilize those for emission spectrum. Anyone online or in person?
Okay, so Dr. Blaine asks, the bscript launches best for the sequence. I don't know, the scripts when you bring this launch, and put next launch, sorry. I guess. My guess would be in the bscript, there's a order, or so it's going to stay in there until its calculations are done or cut off by the compiler.
Yeah, if it wouldn't be so, then there will be big messes of results. But each submission of job scheduler at NERSC generate this SLURL file, which writes down all outputs. And if one follows it, one does see that it starts fast, it finishes fast, then starts like couplings file, then starts fast again. If it would be violated, it would be a mixture of those outputs. And I'm asking because, like, in the previous version of the spots, even before NERSC was deployed, it was problematic to make it happen. In very early versions, several instances of bus were launched and conflicted with each other. Now we don't have this problem.
Was my biggest fear on the way to compete is non-adiabatic couplings, which errors you advise salt to avoid. I guess one of them was, I guess I tried just picking out what I needed. So I guess in this file where I was like, things you need to copy, I didn't realize I still needed pop cars. So I think that was one of the main errors that I had to be aware of. I guess. Yeah.
Okay. So if anyone tries and experiences errors or failures, just maybe let's share an email to the whole group, and then we will answer to everyone, so we will fix errors quicker. I bet there will be several errors placed from several practitioners, but they're fixable, right? Okay. There's a question from Sean.
And you translate passport, we also need a load passport module. I don't think so. I guess I'm not sure. I mean, one way around that. I guess one way around that, you can just comment out the fast, whatever it is in general, and we'll just learn to make it work. I don't know. Any thoughts from those more experiences with fast?
shown but before is not needed. The version of script which was very successful, outcard to postcard, was written for VASP4. And just to use this efficient version of script, we need to downgrade format of postcard, but the rest is not needed. We are happily using VASP5 because it is more efficient. So it's only a question of format and only one script. For the question, the answer is satisfactory. Okay, more questions to Hadassah? Yes.
You mentioned MATLAB again.
Yeah.
Do you use MATLAB to extract the data?
Okay, yeah.
Oh, sorry.
Yeah, I guess I didn't know that. I was also kind of going off presentations from last year. It's like, oh, so extract the data. How do I do that? So I didn't have MATLAB before, so I did these things. But yeah, I think like in sense can be covered next week. So
The archiving of couplings is optional. It was added to the very latest versions just to make files a little bit more condensed. But one can either unzip them on your local computer, or one can remove this archiving in the script if you don't care about space. It's not a major thing. More questions, one? More questions, two? More questions, three? So next presenter is Landon, who served as a host for the first 5 minutes of this meeting, and who was already credited by some of the speakers.
All right, can you hear me?
Yes.
Okay. So, I have a bunch of Zoom stuff in my way here. All right, so I guess, yeah, this is going to be a little bit more, kind of a loose walk through the theory of like why we need to keep rerunning VASP over and over and over again for every one of these time steps. Because basically we need to get particular information out of that WAVECAR file. So probably want to know what's in the WAVECAR file. And if you look at the VASP wiki page, this is the information that is stored in it, but you're not going to be able to just open up this file and look at it because it's a binary file. So the only way to really read this data, since it was put into binary through Fortran, you're going to want to read it back out through Fortran as well. And that's why we use these Fortran scripts to do this. So really what we're after here are the wave functions. And by the way, if you're ever confused about like, something that VASP does or like, variables or whatever, I would highly recommend this wiki down here that has done me a lot of good a lot of times. And that's where, this picture is taken from. It's just the WAVECAR page on there. So yeah, why do we care about the WAVECAR files? They hold the wave functions and we need those. So the way that VASP usually runs is that it's trying to converge toward equilibrium. And in an equilibrium geometry, or like in the ground state, the wave functions are all orthogonal. And so effectively what that means is that we can't have any transitions from one state to another. And so the system isn't really going to do anything electronically speaking. So we don't really want that. So we need to get around that somehow. So we do our molecular dynamics run, right? And that means that all of our molecules are moving around and changing positions constantly. So if we look at, say like the 134th time step and the 135th time step, the nuclei will be in slightly different positions between those different snapshots. And that means that if we compare the orbitals from, say the 134th snapshot and the orbitals to the orbitals from the 135th snapshot, those orbitals are no longer orthogonal to each other because they'll be slightly shifted because of the change of the nuclear positions. So what that kind of means is that these orbitals will, sort of overlap each other just a little bit. And that little bit of overlap is what we need to get an electron to move from the one orbital to the other. So how do we actually utilize that? Sorry, trying to zoom stuff out of the way here so I can see what I'm looking at. So basically we have these, big long integrals that we don't want to do. So we just have a supercomputer do them for us. So this Vij quantity, this is a measure of like how much the orbital I and orbital J are overlapping each other. So this is sort of a quote unquote simplified version of like the one that we actually do. So this is just saying that we're integrating over space. Don't really worry too much about that. This is the ith orbital from the first snapshot, and that depends on where we're looking and all the nuclear positions. This is the jth orbital from our second snapshot, just spatial coordinate again, and then positions of all of our ions. So if we shift one of those ions just a little bit between our time steps, that's going to alter our orbitals. And now that will make this integral, I guess, not equal to the Kronecker delta, right? It's not going to be 0, assuming that these are different, and it won't just necessarily be 1 if these are the same. We're going to start to kind of take, more or less continuous values here. And let me know if this kind of doesn't make any sense. So yeah, so like in this case, right, like these wave functions, they depend on like all the positions of our nuclei. And so like here, we're just assuming that we'd move 1, right? And that's enough to change it. But in reality, that didn't work. There we go. All of our nuclear positions have probably changed. So this is basically the same thing as that last one, except instead of it being just this one thing that has changed, every nuclear position has probably changed now. But otherwise, this is the exact same thing. We're just looking at, the ith orbital from our first snapshot and the jth orbital from our second snapshot. And now these orbitals can kind of intermix a little bit. And this quantity is sort of how much like space they share. And so, so once we have that, now our electrons can transition from state to state, so we can do electron dynamics. And that's what we're interested usually when we're doing dynamical things. So my experience with this is, using red field theory. So this is the red field tensor. Don't worry too much about this. You got all these gamma things, blah, 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 blah. But like the V's are used to calculate these quantities. And so that winds up giving you this red field tensor, which the values more or less tell you how readily an electron will transition from like one state to another. It's something to that effect. And ultimately, we plug this into this thing down here, solve this whole equation, and that will wind up giving us the time-dependent electron density of our system. So this quantity here is really what we're after for electron dynamics. So this is telling us how the positions of the electrons are changing with time. And that can give us transition rates. Okay, there we go. So in order to calculate that sort of stuff, that's what we use the bscript for. I just pulled the first one that I found. They all generally do the same thing, but they're going to look a little bit different depending on the details of like, which version of VASP are you using? Are you using like closed shell, or are you doing non-collinear spin? So you're going to have to probably dig around a little bit and find the right bscript for what you're trying to do. But the general structure is that you're going to loop through all of your what am I trying to say? Like your snapshots of your nuclear positions, like all your different time steps. So that's what this whole for loop is doing. This might look kind of weird depending on if you've ever done like any shell coding. This is just formatting it so that basically the script will say P005 instead of P5, because that's the way that our files are organized. So that just makes stuff work. Excuse me. Oops. So This is just copying our WAVECAR file to a different file, because when we rerun VASP, it's going to overwrite the WAVECAR file. So we're ultimately going to be comparing this one to the WAVECAR file after VASP is run. And that will give us, you know, our first time step, second time step. These P whatever files, these are really just postcar files at that particular moment of time. So before we run VASP, we want to make sure that we copy the appropriate postcar file like into what VASP will read as the postcar file. Otherwise, we're not going to have our nuclei in the right positions. You might want to take a look at these things before you get too carried away. This basically changes which style of VASP you're running. The ones that I'm aware of are this one, which is gamma, there's standard, which is STD, and then there's NCL, which is non-collinear. So if you're doing closed shell, you probably want to do either gamma or standard. But if you're doing anything, you know, if you have spin up, spin down stuff separate, you're going to want to do VASP, NCL. I think gamma can do some of that too. I can't remember. It's been a while. But you're going to want to make sure that you check this as well, because this is telling you how many cores you're running your program on. And that needs to match up with your nodes that you assigned in your, it's not the SBatch file, but it's the one that's got, you know, # SBatch, whatever, # SBatch, whatever. Just make sure that you kind of look at, like, you know, either the Nice Landing, Haswell, whatever architecture, and make sure that this is appropriate. I don't think that you actually need to change that one. Yeah, you start running stuff and it's going to start running other scripts. It's not always going to be the same scripts. That's something to kind of keep an eye on, because you might need to change which scripts it's running, because the directories might be different. You know, I ran into all sorts of problems when I was doing this stuff, and I had to recode things. So it was just keep an eye on it, make sure that things are actually lining up correctly, and make sure that this file is actually in that directory. So like these ones will actually use the information from the WAVECAR files. But these are going to be Fortran scripts, so you know, I don't know, you might have to look into those. Oops. And just make sure that those are working right if you're getting errors. And then ultimately what we get out of this is these coupling files, and these contain this information here. So basically you set it up to go between, you know, all the orbitals that you're interested in, whatever that range was. And these coupling files will have all of that data inside of those. And then I've got to move my thing again. So the way that it actually gets calculated, like there's a overlap.f script. There's actually a few of them, but they will have usually some function written inside of them. And this is sort of the function that starts to calculate non-adiabatic couplings, hence the NAC. If you've never used Fortran before, these things are just to indicate that you're doing a multi-line command, so that, because it doesn't end with semicolons, it's just kind of it's an old school language. This is one way to comment. This is another way to comment. There's a bunch of other stuff too. If you ever have issues and have to recode stuff, feel free to ask me, because I've had to do that before. But yeah, so this is, you can find this one here in that particular file. And, you know, you've got all these different input variables here. Basically, this is your first one. This is the second one, right? First one, second one. If you see the DT, that basically means that that's your second snapshot. Oh, come on, there we go. This is just some more raw code from there. This is the end of what we were already looking at. And then this also calculates like non-adiabatic couplings is sort of the next step of that. And so this thing here is equivalent to this part of that equation that we were looking at. This part here is equivalent to this part of that equation that we were looking at. So this is sort of where the actual calculation happens right here. So yeah, you may wind up needing to kind of recode things a little bit. So just kind of useful to know where that stuff is. And this is, I guess, just kind of a broader view of that same thing again, without all the stuff in the way. And I think that that is everything. Yep.
Okay, please join me in thanking Malcolm. And let's welcome Dr. Aaron Ford, who joined us this meeting. So we have more and more visitors. Aaron, nice seeing you. Thank you for joining. So let's chase Landon and please him by questions, either from in person, or from online, or from chat line. Joseph?
I hold it pretty low.
Okay.
Raise questions.
Hadassah, do you wanted to chase your fellow physics major?
I guess I want to look at the slides later to follow the whole, but at the moment I can't think of a question.
Yeah. I kind of tried to write it so that you could, do that and look back at it. And this paper that I wrote, the way that I wrote up the methods section is, with the intent of it making sense to someone that was, at my spot in my career at that point, because I didn't really have a lot of resources that made much sense to me at that time. So I kind of tried to make it, upper level undergrad friendly. So hopefully, it makes sense on there if you need more, theory background behind it.
I had a question about that equation there.
This one or this one?
The first one.
Okay.
So everything right of the dr, is that also in the integral, or is that?
Oh yeah. Yeah, so basically, yeah.
Okay.
A lot of times you'll see in like complicated integrals, you'll see, your d whatever's right away. And that way you just kind of declare like the thing that you're integrating over right out of the gate, and everybody can kind of see it, instead of, what you usually see in like math class or whatever, where you have the d whatever at the back.
Yeah.
But it's the same thing, it doesn't matter.
Yeah. Got it. Thank you.
There was a question from Lola in the chat line.
I am just opening that up right now.
So it's an unbiased question.
Okay, so Lola's question is, I'm not sure how I get the idea of the WAVECAR and WAVECAR old files, because I know the WAVECAR old file does not get saved. So I guess what I should say is that, like, in these scripts, you're going to wind up reading data in from the WAVECAR file and the WAVECAR old file. So the idea here is that we're dumping all of the WAVECAR data that we did have into a different file called WAVECAR old. And that way, when we rerun BASP and it, overwrites whatever file was called WAVECAR, we still have our old one around. So like this one would be our electronic states from, say we're at like the 5th time step before we run BASP, right? So this would be the electronic structure at the 5th time step. And then once we run BASP the next time, we'll have regular WAVECAR, which will be the electronic structure at the 6th wave step. Then we run these scripts and we have, our 2 adjacent time steps. And then we can do this sort of thing with it. And then the next time we go around, it'll get overwritten with the 6th time step, but then BASP will run and then we'll have the 7th one. So that way we always have sort of the 2 that can piggyback off of each other, and we can always compare the orbitals of adjacent time steps.
Okay, thank you.
Dimitri is asking, what is the meaning of the curly brackets? I'm assuming these curly brackets. So this is just saying that this is the set of all of the nuclear positions at this time. So instead of writing it like this, which is a more explicit way of doing it, we just say like lump all those into this set. And then likewise, this is the set of all the nuclear positions at the time, t plus whatever our time step is. So the next time step. And Dimitri is asking me to clarify if I am teaching spinless or spin polarized versions of the codes. The one that I had pulled up is spin polarized. So essentially this block is the exact same thing as this block, but this one is dumping stuff into, like this is for spin up things and this is for spin down things, but these are doing the exact same thing. They're just putting them into different places, namely these up and down directories. So if you do a spin restricted one, you'll basically only have one of these blocks. It'll probably look a bit different because you're not going to use this exact script because this is spin polarized and you don't need that. But yeah, so this is kind of where you want to keep track of like which bscript you're using, because if you use the wrong one, it's just going to error out. Nothing's going to work. And how is the overlap procedure programmed in Fortran? Is it possible to wash the lines of the code?
I think you already you did show it.
Yep. Yeah, that's this part right here. And then you could watch it if you want. You'd basically put like print line statements into this code, and then it would start spitting everything out onto your terminal. And that's useful for like debugging, making sure that things are reasonable. And then if if you bump into errors or whatever, you kind of see where it happens. Okay, and that is the end of the questions in the chat line. Does anyone else have any questions?
Oh, yes, there is one.
I do not see it. My chat thing disappeared on me now because I closed it. There we go. So when reading the V sub ij in Fortran, is it truly an imaginary value or is it assumed to be imaginary and has a real value? I guess I would have to dig into the code more, but yeah, because Fortran can handle complex numbers, so I don't know why we wouldn't be able to do that. Because once we have computed this integral, like this value should be imaginary and this value should be imaginary, but this value by the time we're done should be real. But there might be some tricks in the code that I would have to look at where maybe these are actually just kind of, real, but close enough to the actual value after we do all this that this is effectively the same.
There are tricks, and maybe Aaron wanted to give. Aaron, do you want to answer your question yourself, or you were just giving chance Landon to try?
I guess it's something I don't truly know myself, but I've been playing with the code, and it's something to keep in mind if you're trying to like make sure your calculations are accurate, or like what you're computing. There's like the types of the variables.
Yeah. Well, because I saw that there were complex variables, but I was just skimming through stuff pretty quick, so I wasn't really paying that much attention. But I know that the scripts do save at least something to complex variables.
Okay, I will give partial answer, maybe incomplete. So how do we know which of the orbitals I or j should we evaluate at the incremented time? Should it be time increment for j or time increment for I? And if you're not sure, probably we should do both. So the one that you wrote, plus the one where you put dt into the I wave function and no dt into j wave function. And then you can average between them.
Yeah.
And when one does this trick, then imaginary, one makes rotation in complex plane 1, way, another does rotation in other way and direction, and when one makes an average, imaginary part disappears and Vij will be real.
Okay.
And
Yeah, that makes sense to me, I guess. That's clever. Yeah.
And the credit the author is to John Talley, who is likely retired now, and Sharon Thomas Schiffer, who is active now, and I don't know. She was jumping. She was invited from one top university to another one, like from Pittsburgh to Urbana-Champaign to Yale, and maybe she either at Yale or promoted even higher. But this symmetrization of non-adiabatic couplings was designed like in 1995. Aaron, are you satisfied? Oh, okay. Let's check if you have more questions to Landon. One, questions two, questions three. Please join me and thank you Landon once again. So we have 3 more talks, which could last as short as 15 minutes or as long as another hour. Let's see. So next presenter is Amara Arshad, and she will refresh our memories on practical steps to run spin-less non-adiabatic couplings. Amara, would you like to share your screen?
Yes, sure. Can you see my screen?
Yes.
Okay, so I will talk about the setting up of input parameters for the non-adiabatic coupling without spin, with spin, and with spin orbitals. So first, after the molecular dynamic simulation, we move towards the coupling directory, which contain all the generated files from the MD calculation. And here, when we run this Perl script, and we will get the snapshot of the snapshot of these files during the MD simulation, and we will get as explained by the previous speakers. Then we need to calculate these files, energy pop input overlap file that we get from the geometry optimization and by running the Perl script. And for the in-car file, we need the in-car coupling file that gives us the information about for the non-adiabatic coupling without spin. So this is the file format for these are the file format for the that we extract from the intermediate geometries, and this is just a example of one file format. It is like the postcard file, and when we have to use it as the input for the postcard, then we need to delete this line, these atom lines. So this is the file that extracts the atomic configuration at each time steps from the outcar file. And these are all the input parameters that we need to run the non-adiabatic coupling, input overlap file, in-car, K-points, port car, and these intermediate empty trajectories. And beside this, we need these executables into our directory, and then the bscript file that is explained by the Landon in the previous talk. So this is the format of the bscript file without the without spin, and here these are just the information that are explained by the previous speakers. That we this is the time step here. We need to mention the time steps for our for the MD trajectories that we use, and we need to specify the postcard file, the name of the file, and And here, these are the executables that we need to provide in our directory. And when we run the script, it will give us the output files in the format of the coupling files. There are in the output files. And these coupling files gives us the information about the transition probability from the one orbitals to the other, and that is in the form of the numerical matrix. So when we run the non-adiabatic coupling with the spin, everything will remain the same. We just need to provide the bscript that gives the information about the up and down. And this is the example of the bscript. The other parameter will remain the same. So for the non-adiabatic coupling with spin orbitals, the non-adiabatic coupling spin orbitals calculation are built on the molecular dynamic with spin orbit calculation. This kind of calculation is very expensive. Therefore, the spin polarized molecular dynamic is used. We need the output files from the spin polarized MD calculation. We need these files input overlap and the snapshot in intermediate geometries file and the in-card coupling file. So this is the bash script for the spin orbitals, and here we need this executable into our directory to run this non-adiabatic coupling with a spin orbital, and the other format will remain the same. And when we run this script, so we will get the output coupling files in our output directory. So that's all from my side.
Okay, please join me in thanking Amara. So many thanks for this nice summary. So any questions from in person, from online, or from the chat line?
So you mentioned we have to do this spin polarized calculation first. Are you saying we have to do the spin this last slide calculation before previous slide calculation?
For the spin orbital?
Yeah, so like you have to run this whole coupling calculation for the spin polarized before you run the coupling for the spin non polarized, or
yes, I am not sure, but I think that we need the output from first the spin polarized calculations after the MD.
Oh, okay, those. Yeah. Thanks.
Okay. Are there more questions? Let's look from the chat file. Well, those are biased questions.
I'm not sure about the YH in the script.
For the first time, where can I get this scripts? Are they stored in a specific directory?
Yes, I get it from the bin file.
Is everyone agrees, or there is something more specific?
I can tell you that the spin orbit is more specific.
Okay, then it tells that codes for spin orbit have more detailed directory. Okay, and maybe it will
some of them, not all.
For some of them, so maybe it will tell in the book. And yeah, what does YH is in the name of the script?
Why I'm not sure about this. It is for the
I think Sarah wants to answer.
Yeah, it means Yulun Han. The script is provided by Dr. Han. I think maybe some modification for that.
Okay, very good. Are there more questions, Amara? Questions one, questions two, questions three. Let's thank Amara once again. So we have two talks more, and the next speaker is Sarah. So Sarah will give us a detailed overview of spin polarized spectra and spin polarized non-adiabatic couplings. And as you have seen before, we look on spectra first and coupling second because they have some similarity in equations how they are formulated. Okay, Sarah, please go ahead. I'm looking forward to it.
Thank you, Dr. Green. I think everybody explained the work that I'm going to present, so I will quickly show it. So I'm going to explain how to plot the absorption spectra for different spin components in a case of spin polarized. So the file that we require for plotting the absorption spectra are postcard, key points, outcar, wavecar, podcar for the for the optimized geometry. Then the first step is we need to create a file, as others explained, input overlap and set the range of orbital energy that we want. We repeat it twice because we have two spins, spin up and spin down. And also we need to specify a placeholder, number 1, at the last line. Then we need to run this executable in order to extract the energy pop files for the spin up and spin down. Next step is the actually run these two executables to see the transitions for the spin up and spin down components, and it will gives us the OS strengths and OS strengths down files. So it's better to maybe rename the name of the OS strengths file to OS strengths up. Maybe it's kind of easier, but it's a personal choice. Then we need to extract the occupied to unoccupied transitions from 1 to 0 from each of the OS strengths files and put it in another file called OS up and OS down. So here, after copy and pasting the OS strengths up file into the OS up, we need to specify the number of transitions for this component or the alpha component, and then execute the following code. So in this code, it requires number of transitions, which I said we need to count the number of lines of the OS strength file, and then the range of energy that we want to plot the absorption spectra. In this case, I chose just 0 to 10 electron volt. The width of each line, as well as the number of the HOMO orbital. Then we can use the GNU plot command to generate the absorption spectra as a function of energy and as a function of the wavelengths. And then by using the last comment, you can just convert the file to the PDF format. And here you can see this is the absorption spectra for the alpha component. For the beta component, everything is the same. Just you need to copy and paste OS down, as I explained before, into the OS strength file, and again execute that command and count number of the each live OS strength file lines, and then using and enter the number of HOMO again for the beta component, and again using the GNU plot command, you can generate these plots for the beta component. And then for the non-adiabatic coupling calculation, as Landon, Hadassah, and Amara explained, this is the case for the I am explaining for the spin polarized case. So after heating and the molecular dynamics, you need to copy outcar, key point, postcar, and podcar, as well as the input overlap and the incar, Cori.sh and the BS script file into another directory, maybe non-adiabatic directory, maybe, and then execute the following command again to generate the different snapshots or the files that already explained by Adam, maybe the P00, something like that. Those files you can generate with this executable. And then also, as others explained, you should notice that the postcard file is in the WASP4 version. And then you need to, as Amara explained, this is the BS script provided by Dr. Han. These are, it says that, for example, create a directory called up and another directory for the spin down. And you can here specify the range of energy and or the range of time step that you require, that you want. And here the top, this part is for the spin up and this part is for the spin down. So it's automatically generate the energy pop, extract the energy pop files for the spin up and spin down, and do the calculations for each spin component. So if everything it goes well, you can see the coupling files generated in each directory for spin up and spin down. So on these, the data for different spin components are kind of different from each other. They are not the same. So that's it.
Okay, please join me in thanking Sarah.
Thank you.
So any questions in person, online, or in the chat line?
So for the chat, you asked why input overlap has 5 lines instead of 3. So I said that because we have 2 spin components, spin up and spin down. So 2 of them are for the spin up and 2 of them are for spin down. And the last line is for the placeholder. And another question, which system is?
I want to say that homo for spin up and homo for spin down may not be equal.
Yes.
Yeah, thank you.
Yeah, here as I said, for example, this one is for the spin down, it is 194, while for the spin up, it is 195. So another question is, which system is used as an example? Just curiosity. It's the Clay system for the n up down equal to 1.
Thank you.
Yeah.
Any more questions? Sir, I'm expressing curiosity in a couple of other questions.
In the chat?
Yes.
Okay. In which situations one needs spin polarized calculation and one can make the I think it depends on the type of material and the system. For example, when we have the transition metal atoms, maybe we need the spin polarized calculation.
Okay, so you want to say that if there are unpaired electrons, then one needs spin polarized.
I guess.
Okay, and then the next question: when spin polarized is insufficient and one needs something upgraded, like when does one need spin orbit coupling?
I'm not sure. Maybe when I think it depends on the accuracy that we want from the system. For example, when for the spin orbit coupling calculation, it kind of maybe it's more precise and more expensive maybe.
Which process is forbidden in spin polarized calculations? And Hanman, please try to think about it. If you do not want to answer, if you don't have answer, do not reply, but just try to think. And it's a question to everyone who deals with transition metals. If we all fail to answer, David likely will provide an answer. He speaks next, but which not quantitative improvement of precision, which qualitative process is not available in spin polarized calculations?
The kind of the interaction between a spin and the orbital, something like this, yeah?
Right. So let me show.
You mean the angle of the maybe electrons, it's just maybe up and down. Maybe in the spin orbit, it has another angle, maybe 45 degrees, something like this.
So, Hanman, what is the main excitation of your system? And I know also that Adam knows the answer. So, what happens to the spin multiplicity when you go from your ground state to excited state in your manganese dope?
Different splitting happen.
Do you have the same spin polarization before and after excitation, or it changes?
It changes.
Okay. Sarah, does it give a hint? So in your publication, you separately considered low spin, intermediate spin, and high spin.
Yes.
And the calculations that you did were independent. There were no transitions between low and high spin. And spin orbit coupling does allow natural conversion between them.
Mm-hmm.
Adam, do you want to add anything? Sure. Triple. Okay. Okay, yeah, thank you.
I see, thank you.
There was a question from Aaron in the chat room.
What to do with all energy pop and OS files generated? I'm not sure about the energy pop files, what we do, but for the calculation that we did, we just used the energy pop that actually generated from the geometry optimization. So maybe here I saw that in this file, the energy pop here, it says remove this file. I'm not sure. It's a good question. I'm not sure about the response for this question, the OS file generated. And
Sarah, would you please show the list of files generated maybe in the next slide?
Yes, here.
Yes. So here there are oscillator strengths computed at each time step.
Yes.
And I believe Aaron is asking, why do we need them? Can we get anything good out of them?
You mean for the plotting the non-adiabatic calculation, kind of the plot that we had, for example, from HUMO minus 17 to LUMO plus something, the different transition, kind of the evolution of the energy in the time, or the evolution or the dissipation of the energy in the time, maybe using that red field tensile energy. It kind of needs this file. I'm not sure how to explain it.
Yeah, thank you. Aaron, are you satisfied or you want to hear more?
I guess I would say that like within the group, there's no standard way, but like usually a good practice is to like take the average, at least for the energy pops anyways, to like average those, since like each one of those files is one step from the molecular dynamics. And usually it's like what you see in experiment is an average value. So you can take the average of all the energy pop files, and you can either take the average of all the OS strength files or just combine them into one big file and plot the spectra that way.
Yeah,
So those are
exactly.
two possible things to do with all these files.
Mhm. Yeah, exactly, because our resources kind of is limited, so we run the simulation for kind of limited femtosecond, and then we may predict how the simulation or how the system goes, the energy of the system, for example, goes by using that Redfield tensor equation. So it needs these OS strength files, or the, as you said, or by averaging from these energy pop files. Am I correct, Dr. Han? Dr. Green?
There is additional ways to do Redfield dynamics. Plus, there are some additional methods based on this data that you will maybe in 3 weeks.
Yeah.
Okay. More questions to Sarah? Questions 1, questions 2, questions 3. Thank you very, very much. It's really, really good.
Thank you.
Now we have the last but not least presentation by David. So if you have accumulated some questions that you hesitated to ask to previous speakers, dump them onto David when it will be time for asking questions. And probably he will start his talk with introducing the, like repeating once again, in which situations spin polarized is insufficient.
So I guess I can start there. So you want to use spin polarized when you have unpaired electrons. So anytime you have multiplicity or doping or anything along those lines. Spin orbit coupling is the major thing that allows is spin flipping. You're going to need it primarily when you have heavy elements as well. So as for generating the coupling files and spin orbit coupling, these are all the files you need. So you need the input overlap, which has been described a few times. I think I have a thing here for it. No, I don't. The Zoom was covering it. I thought I did, but then you need the PXX files, which have been described how you get them from MD. Then you need the spinner.ex with file which generates coupling, the oscillator strength underscore spinner ex file which generates oscillator strengths. bscript, you need two different incars for this. You need the incar underscore SP or NSP, depending on whether you're running spin polarized or spin restricted calculations for your main. And then the underscore NCL for the non-collinear. And then you need a submission script. Oh, here's where I have the input overlap description. So it's been described a few times, but the first number is your lowest orbital index that you're interested in. The second is the highest, and the third is a placeholder. And then here you see the paths to find these files. Most of them are in the bin or the spinner directory within the bin. You find the two incars within the in-car directory. The input overlap you obviously need to make yourself, and the PXX files are from your molecular dynamics running has been described by Adam, and I think Hadassah also covered how to actually make them. Apparently that's not changing slides. So if you look at the submission script, the major thing that's different compared to our standard submission script is this line right here, the dot/bscript line, where the normal line that you see if you look at these is this srun line that's commented out here. One of the major things to note here is the nodes. So you need to know how many nodes you're doing so you can put the correct number of cores in the bscript file. So here is the bscript file for the spin orbit jobs, and it's a bit long, so I've had to cut it to move it off to the side a little bit. So you can see, if we look at the beginning here, you can see the major difference between the spin orbit jobs and the other ones is that we run, for each step, we run 2 jobs. We run a non-spin orbit job and a spin orbit job. So what the non-spin orbit job is generally a charge car, which we use in the spin orbit job because it tends to create more stable outcomes, work more stably when you run from a charge car. So here I have highlighted these srun scripts, which I pointed out in the submission script. So this 128 here would be the number of cores you would use. And so here in the blue boxes, I'm showing the parts of the script that copy all the output files we generate through each one into something that we save, because they'll, if we don't do this, they'll just be overwritten. And from here, so above this yellow line is our initial round, which I was running apparently 145, starting from P145. So then if we look here, I was going, the next one is 146, and I was running up to 200 in this calculation. So this is what your directory is going to look like once it's done. And you notice we got all these output files. There's the WAVECAR, outcar, couplings, and oscillator strength files. And they have all these .0045 and etc. I have set mine up to output 4 digits. The basic one outputs is 3. So this is what it will look like. You'll just have a string of these for however many you run in that directory. So then if we actually open up the coupling file and take a look at it, you'll see that it's a matrix where the diagonal is 0. So if you look right here at the first line, you see 0 in the first position. And then if we go down about 2/3 of the way down, you see 0 in the second position. That's the second line of this matrix. And that's where my talk ends. So if there are any questions.
Okay, please, Chairman, thank you, David. So anyone is not tired and has energy to ask questions? Okay.
It was in so that you have that yellow arrow that hangs down.
Yep.
The echo line above that. Why do you have that there?
So that echo line, I have added that line so that I can grep S-wave out of the slurm to see exactly where my job ended when it timed out. So it's, if you notice, it's, I have it here right above the yellow line and like 3 lines from the bottom of the thing. You notice it's after the copying the WAVECAR to WAVECAR old. So I know the last WAVECAR that got copied. So when I can start the next submission script, I don't have to dig through the slurm to figure out where it actually finished.
Okay. Yeah. Thank you for the question. Thank you for the answer. Anyone in person? I have a question for Hadassah. David told that heavy elements need spin-orbit coupling. Is cadmium and lead heavy enough to request this form of calculation. Oh, you can redirect my question to the.
I think Bell's lead is, since it's higher up on the periodic element table board, I remember, but.
Lead definitely is. I'm just looking at where cadmium is on the periodic table because I have no idea.
So David himself is studying semiconductors, including lead, and he is an active practitioner of spin-orbit coupling. So initial calculation can be done without, but if you go professionally, you may want to. Let's keep asking David questions. Anyone online? Anyone in the chat line?
So Dimitri asks, where are all these scripts located? Primarily in the bin, in either the plain bin or the in-car or spinner directories within the bin.
Okay, so just look into slide 3 of your presentation.
Yes.
Okay.
What do the notations VC, CC, VV mean? So if we look at this, you see in the oscillator strength files, they all end on underscore VC or CC, or do I have any VV? Yes, I have VV. VV, those are indicating the bands that this oscillator strength file is looking at. So V is looking at valence band to valence band transitions. CC is conduction band to conduction band. VC is valence band to conduction band.
Thank you.
Dimitri asks how to interpret 0 at the main diagonal. So here, if we look at the main diagonal, it's going to be zeros along the diagonal all the way. I just showed the first line and a third. So that's because the main diagonal is going to be the interaction of this one orbital with itself. So you're not going to have any interaction. In theory, it's going to actually be probably infinite interaction, which we then determine state as 0. Because it's a measure of how much they interact or break orthogonality. Aaron asks, why VASP gamma and not VASP standard? To my knowledge, I'm doing this at gamma point only. I'm not doing K points with this. So they should give the same basic results, since I'm not using WAVECAR to help me with the spin orbit coupling job. But there's no reason I couldn't do it in standard. To my knowledge, it's just it was written as gamma when I got the code, and I never cared enough to change it.
What is a gamma point?
So on your pretty little graph that had those colored lines at the end, gamma point is 0.
Oh.
0 momentum, 0 velocity of center of charge, center of mass of orbital. So they do not move, stay where they are. So if you have isolated molecules, there's no chance to periodic metals or semiconductors they can.
All right.
Does that answer your question, Aaron? Or
Yeah, and I guess the other benefit is gamma is generally quicker than the standard executable too, so it saves some time.
And these tend to be annoyingly long.
Okay, let's check other more questions to David. Questions 1, questions 2, questions 3. So let's thank David once again. Very, very productive and inspired session. Many thanks to all speakers and participants of the presentation. I think we went a little too long this time, and maybe we can improve it. So we're looking forward to either 2 or 3 more knowledge transfer sessions, and I suggest doing 3 instead of 2 so that we finish a little earlier. So right now probably everyone is tired, but please try to access this document and volunteer. If after a couple of days I'll try to ask if there will be insufficient volunteers. So let me give a brief overview. Couplings that all of us are expected to compute in the next week. Please try to do your best to compute couplings. If something doesn't work, complain to everyone in this group and help each other. I'll try to help as much as I can, or maybe you help each other much quicker than I can in open the email. And then what to do with the couplings? The goal is to see what happens to excited electrons and holes, excited system, when population of orbitals changes over time. And this is like multi-step procedure. First, one needs to convert couplings into like rates of transfer. And I think if you just look onto this conversion of couplings into rates of transfer, will be enough for one long meeting. Then it will be a little shorter than usual. And then, so it will be meeting number 3. Meeting number 4 will be actual dynamics, how excited electrons, holes change over time. And then the number 5 will be the protocols of extracting observables related to real life. Okay. So I believe everyone needs to just have a fresh breeze and relax, because it was very, very intense. And when we all come to normal, try to look through. I'll try to populate these materials as we did last time, so that you can do educated selection of your choices. Okay, let's thank